In this lab, we observed the motion of a falling object, in this case a volleyball, and used Newton's second law of motion to explain the behavior of the ball. As opposed to a constant velocity example, the falling object is being acted upon by the weight force due to Earth's gravitational pull. To represent the theoretical results of Newton's second law, a computational model was created, which slightly overestimated the actual experimental results, for reasons that will be explained later on in the video. Here's the clip of the experiment in action being analyzed through Tracker. As seen, the initial velocity is 0, and as time progresses, the velocity or the change in position increases, which indicates that the ball is accelerating. A change in velocity means that the net force is non-zero. In order to write the computational model, some key elements must first be understood. The equation for Newton's fundamental principle, as seen here, will describe the behavior of an object in motion. However, the net force in this case is not zero. The force of gravity can be found using the equation above, where mass 1 represents the mass of the Earth and mass 2 represents the mass of the object being observed. However, the mass of the object is negligible relative to the mass of the Earth. Therefore, the above equation can be simplified to the weight force, W equals negative 9.8 meters per second squared times the mass of the object. Here's the code that will model the behavior of the ball as it falls. The computational model runs as follows. The motion of the model and the graph associated nearly match that of the tracker data. When both the graphs of experimental data and the computational model are compared, both graphs exhibit a downward curve shape. The computational model overestimates the experimental data slightly. The most probable explanation for this difference is drag, or in other words, air resistance. Air resistance exhibits an upward force counter to the force of gravity, which would explain why the ball in the experiment has a smaller velocity than the computational model. In order to represent air resistance, some minor changes have to be made to the code within the computational model. The drag force is proportional to the velocity. Therefore, the drag force can be represented by the equation Fd equals negative b times velocity. When factored into the force equation, net force can be represented as F equals W plus Fd, where W is the weight force and Fd is the drag force. Finding the value of b, however, will take some careful approximation and trial and error. In order to find the b value, values of b were estimated and input into the computational model until the final position of in the computational model closely matched the final position in the experimental test. The value of the proportionality constant that was approximated was 0.45. Here's the computational model in action. Here's the new graph of position versus time. As you can see, both the graphs of the computational model and the experimental data more closely resemble each other. However, there are still some sources of error that cause slight differences in the curves. After closely observing the original tracker clip, it becomes apparent that the ball slightly rolls off the hand, which may have slightly offset the velocity of the ball in the initial part of the clip. Also, the last tracking point may have been placed while the ball was beginning to bounce upward. This error makes the final position value less accurate and could have skewed the approximation of the proportionality constant. In conclusion, Newton's second law remains a powerful tool for explaining the behavior of objects in motion, whether these objects are in constant velocity or being acted upon by forces such as gravity and/or air resistance.